Hello everyone. Until now we have considered the step response of the first and second order systems, and we haven't talked about higher order systems. In this lecture we are going to see how we can get a feeling about the step response of systems with more than two poles. Okay, so we are going to consider systems where we have more than one or two poles. We know that when we have a one pole for a system, that system is called as a first order system, and when there are two poles, the system is called as the second order systems. We also haven't considered systems with zeros. Okay, so that's something that we will also have a look in this lecture. So if we consider the general case of a system in the transfer function form g of s as a numerator over a denominator, we assume that there are n number of poles, as you can see here, and m number of zeros. So n is the number of poles for a system, and m is the number of zeros. And generally, for the systems that we consider, we have n bigger than or equal to m. So that's the general case that we have in order to have a system physically indeed realizable. And I can also remind you about the kind of systems that we have. If we have n bigger than m, n equal to m, or n smaller than m, we call this kind of systems as a proper system when m and n are equal to each other, strictly proper system when n is bigger than m, we have more poles than the zeros, and improper when we have more zeros than poles. And that kind of system is not physically realizable. For the physical systems, we never have more zeros than the poles. When we have the system expressed in that form as a transfer function, we can easily figure out the values for the step response of the system at infinity, so the final value, and also the initial value, or c at 0 plus. And you can see here how we do it. Yeah? C at infinity, which is indeed limit of c of t as t goes towards infinity, could be obtained as limit of s times c of s. So this is indeed c of s, as c is equal to g times r, and since we are considering the step response of the system, it's equal to g times 1 over s. So we have g over s equal to c of s as s goes towards 0 plus. And then s at the numerator and the denominator will be cancelled out, and we will get g at 0. So c at infinity will be equal to g at 0. And obviously we have the assumption in mind that we have a BIBO stable system, bounded input, bounded output. Otherwise we can't get the final value, or c at infinity. On the other hand, for c at 0 plus, we apply this rule. So c at 0 plus, which is equal to limit of c of t as t goes towards 0 plus, and it's equal to limit of s times c of s as s goes towards infinity. And again, c of s is equal to g over s, because we are considering the step response of the system. And as a result, c at 0 plus will be equal to limit of g of s as s goes towards infinity. Okay, so we can summarize that. C at infinity will be equal to g at 0, and c at 0 plus will be equal to g at infinity, we can call it, or limit of g of s as s goes towards infinity. So we can have this information for a system of any order, for a first order, second order, and higher order system. So referring to what we have here, we can also say that for the C at 0 plus, for the initial value of the response, if we have a strictly proper system, meaning that we have more poles than the zeros, or n minus m is bigger than or equal to 1, which is referred, n minus m is referred as r, or as a relative degree. In any case, if we have a strictly proper system, then the initial value of the response will be equal to 0. And that's what we had for the first order and second order systems without any 0 in the previous lecture. On the other hand, if we have n minus m equal to 0, so if we have r which is equal to n minus m, and if that is equal to 0, meaning that n and m are, let's say, the same value, are of the same value, both of them are 2, 3, whatever, then C at 0 plus, which is limit of g of s as s goes towards infinity, will be some constant value, such as a, okay, which will be different than 0. In such a case, we will have a jump right at the beginning of the response at time equal to 0 plus, because we assume that before t equal to 0, we have the response equal to 0. So C at 0 minus is equal to 0, let's say. And then C at 0 plus will be equal to A, meaning that the response will be discontinuous. So if this is A, then the response will start from here. So it will not be continuous. Okay? So that's what happens when the number of poles and zeros of the system are the same as each other, or the system is proper, not strictly proper. And obviously, when we have an improper system, we will not indeed care about the response of the system, because those kind of systems are not physically realizable. Another information that we can get by referring to the transfer function of the system is the C dot at 0 plus, or the slope of the response right at the beginning. C dot at 0 plus could be obtained by taking the limit of s times g of s as s goes towards infinity. We know that C at 0 plus is equal to this limit. So C dot at 0 plus will be equal to the same limit multiplied by s. And therefore, we will have a feeling of how the step response will behave right at the beginning at 0 plus. Keep in mind that if r is bigger than or equal to 2, then and this applies to the strictly proper systems, obviously, then C dot at 0 plus will be equal to 0. Otherwise, it will have some other value. If r is equal to 1, there will be some constant value, and if it is equal to 0 for the proper systems, we already have seen that the response will not be continuous. And we also have seen this case, C dot at 0 plus equal to 0, for the second order systems with no zeros. So second order systems with no zeros have this case. The derivative of the response at time equal to 0 plus is equal to 0. So that this is kind of the information that we can get by looking at the transfer function of the system regardless of its order. But this information isn't enough in order to analyze the step response of the system. We will not have enough information regarding the transient behavior of the system particularly. We might know how the response will behave right at the beginning at 0 plus. We may have the information regarding the steady state behavior, but we don't know how the changes will happen from the 0 plus until infinity. And having a general case for the systems is not easy, let's say, for systems of different order. However, in practice, we have the case that many systems behave not very differently from those that we have seen so far, meaning that the first order systems and second order systems. We already know how they behave, the first order and second order systems, and now we are going to see what happens when we have a system which has more than 2 poles. So we will consider a second order system, and then we will add a pole. And we will see how this additional pole changes the behavior of the system. And later we will add a 0 to the system, and that this will apply to both cases. For the first order and second order systems, we will introduce a 0, and then we will see how this additional 0 changes the behavior of the system in terms of the step response. And then we will see that in some cases we can approximate the system as a first order or as a second order system, and then it will become easier for us to analyze the behavior of the system in general. However, before moving forward and considering these cases, let's go through this example. We have the 3 transfer functions given, g1, g2, and g3, and we want to find out c at 0 plus, c dot at 0 plus, and c at infinity, and we assume that a unit step is applied as the input. It should be pretty straightforward to go through this example indeed. As we know, c at 0 plus is equal to limit of g of s as s goes towards infinity. C dot at 0 plus is equal to limit of s times g of s as s goes towards infinity. And c at infinity is equal to limit of g of s as s goes towards 0, or we can simply write down g at 0. Now we can do it for each one by one. For g1, in the case of g1, c at 0 plus is equal to limit of g as s goes towards infinity, and we can see that it will be equal to 0. Because we have 3 poles, there are no zeros. As s goes towards infinity, it will give us 0. C dot at 0 plus for this system will be also equal to 0. Because we will have the limit of, for c dot, we will have limit of s going towards infinity, 12s over 3 terms. And this is equal to 0. And then c at infinity for the system will be equal to g at 0, and that's equal to 12 over 6, which is equal to 2. And similarly, we can do it for g2. In the case of g2, c at 0 plus will be equal to 0. C dot at 0 plus, so I write it for g2, we will have limit of s going towards infinity, s times s plus 10 over s plus 1 times s plus 2 as s goes towards infinity, and this will be equal to 1. And finally, c at infinity for this system will be equal to 10 over 2, which is 5. Basically, it's equal to g at 0. And finally, for g3, c at 0 plus is equal to limit of g of s as s goes towards infinity, which is equal to 3. So we have a proper system indeed, yeah. We have a proper system. If I want to calculate c dot at 0 plus, we will have limit of s times g of s, so 3s s plus 100 over s plus 10 as s goes towards infinity, and you can see that this will give me infinity. Okay, but we need to keep in mind that c at 0 plus is equal to 3. So for this system, the step response is not continuous at time equal to 0. It was 0 here, and then suddenly it jumps to 3, and it continues. So right at this t equal to 0, we have a discontinuous step response for the system. That's why we can say that c dot has a bounded value, let's say. And finally, if I want to calculate c at infinity, we will get g at 0, and it's equal to 300 over 10 or 30. So the final value for the system will be equal to 30 in terms of the step response. In the next lecture, we will see what happens when we add poles to a first order system, which then will be a second order system, or what happens when we add a single pole to a second order system.